Hey, what's up, guys? Yeah, so today, this is my casual talk, because I somehow make some video which is some very difficult. So I want to make some casual talk, and introducing. So this video, I want to introducing ABC conjecture. So which is the preliminary version. So we will not involve many difficult number theory, but give the statement in some application of these ABC conjectures. Hope you guys subscribe to my channel. Okay, so let's start. Okay, so let me first give the definition. So one important definition in the abstract algebra is called radical. Okay, so radical of any integer n, let's say n is greater than 1, is defined to be the distinct prime, the product, I should say, the product of distinct prime factors of n. For example, let's say radical 10 will be 2 times 5, which is 10. And the radical 100 will still be 2 times 5 equals to 10. And the radical x 3 to the cube, 3 to the square, 5 to the 3, 7 to the square will define to be 3 times 5 times 7. Okay. And obviously that radical of n, that's equal to n. Okay. Okay, so now we are able to study the ABC conjecture. Okay, so ABC conjecture, which is very, very deep conjectures. So deep that very nobody understand actually have the proof. Okay, so there are two statements. Okay, so yeah, so the first statement, I should say statement 1. Okay, so in my video, I always assume that A, B are greater or equal to 1 and C equals to A plus B. Okay, so everyone is positive integers. So statement says that for all epsilon greater than 0, there exists a C epsilon greater than 0, such that for all A plus B equals to C, for all triples, so let's triples ABC with this property, we always have the radical of C. Radical of ABC greater than C with the coefficient 1 plus epsilon, and then there is a C epsilon. Okay. Okay, so basically or I can write C less than C epsilon radical of ABC 1 plus epsilon. Okay, and this statement has some version. Let's say let's say the equivalent version. So this is statement 2. So statement 2 says that for epsilon greater than 0, the solution such that C greater than the radical of ABC 1 plus epsilon has finite solution. So it means you can only find a finite solution, right, for this one. So you can easily say that the statement 2 is the same as statement 1, right? Because in a statement 2, if you only have finite ABC triples satisfy this equation, then you can pick out the largest ratio. So you can pick out largest ratio and set it to be C epsilon, right? So you prove that statement 2 is the same as statement 1. Okay, or since you can start from statement 1 and prove for statement 2. Okay. So why is intuition? Okay, so intuition means that this intuition is very, very weird. Let's maybe see some example, right? So for example, let's say 10 plus 5. By the way, ABC should be coprime. Yeah, I haven't measured it. AB should be coprime. Otherwise, that you can pull out the same factor. Right, so for example, let's say you use 10 plus 3 or 13, right? So the radical of the will be 10 times 3 is 13. Will be radical of 2, 5, 3 is 13, right? Definitely larger than 13. So it makes you imagine that suppose you take two factors with the no other no particular prime factors, then their addition should give you more prime factors, right? So that means this radius C should contain more prime factors. Okay, probably this is very not easy to understand, right? But for example, let's say if I take the 2 to the 10 plus 3 to the 10 will give you 6673, 60073, which is 13 times 4, 6 to 1, right? So this is prime. Okay, so if you believe this conjecture, right? So you imagine, so you get right. So the radical will give you 2 to the 10, 3 to the 10, and at least, right? So in order to make this guy greater than this, guy, it seems like that you need some large prime factor here. So basically, you can take the two small prime number and then make the power, and addition should give you a large prime power. This is the intuition. Okay, but so before I go into talk about implication, let me explain why epsilon need to be greater than 0. Okay, so this is the famous results. So ABC conjecture fails at epsilon equals to 0. Okay, so that means there exist infinite ABC pairs such that A plus B equals to C, and the radical of ABC equals to C, or less than C. Okay, so this is the famous results I think need to be mentioned. Okay, so let me just quickly give the proof. So basically, that's why epsilon need to be greater than 1. Okay, so I think this is very old. Let's say K is greater or equal to 1 and A is 1, and you pick C to be 3 2 to the K, and the B divided with C minus 1. Okay, so you can easily check that there is a lemma says that 2 to the K plus 2 divides 3 to the 2K minus 1. Okay, and this can be proved by using the induction, right? So 3 to the 2K minus 1 can be written as 3 to the 2K minus 1 and 3 to the 2K minus 1 plus 1, right? So this will give extra two factors. So you can start from the K equals to 1 and prove this is true, and then you can use this induction. Okay, so which tell you that if you compute a radical, you will get the 3 2 to the K times this 3 2 to the K minus 1, right? But this 3 2 to the K is the same as 3, right? So it comes 3. But this guy will less or equal to 3 2 to the K minus 1 divided by 2, because it divided by 2 to the K plus 1, right? Because it at least has these prime factors. Okay, so obviously that this guy will less than 3 2 to the 2K. Okay, so this is C. Okay, so from here that we know that ABC conjecture is not true for epsilon equals to 0. Okay. So, but up to now, there's no proof for finite epsilon. So maybe maybe ABC conjecture fails for some particular epsilon, right? But my belief is, but the usual consensus is that for any epsilon greater than 0, this should be true. Okay, so let's talk about some applications. Okay, so there will be sometimes if you assume that explicitly conjecture, then you can get something really amazing. For example, let's say suppose epsilon equals to 1, C epsilon equals to 1 is true. So that means for any A plus B equals to C pair, the C always less than a radical of ABC squared. Okay, so if you believe this is true, then you can prove the following. So if you assume this is true, then xn plus yn equals to cn. So basically, then the Fermat, that's theorem, works for n greater or equal to 6. Okay, so basically, if you assume this is the explicit conjecture, then you can easily prove that Fermat last theorem was for n greater or equal to 6. Okay, the proof is very easy. Suppose this is true, then you will get z n less than the radical of xn, yn, zn, which is radical of x, y, and z, but less than what? Less than z to the cube. Z, right? So this then square, right? Square. Right, so it's z to a 6. So which prove that n should less than 6, right? So, but you can easily prove that n equals to 4 and n equals to 3 and n equals to 5 are already proved in the history. And these are very easy. So you don't need the Wiles proof. You can only use the elementary number theory to prove 3, 4, 5 is correct. So this is easy. Okay, so if you assume that this, then you can easily prove that Fermat's theorem is true. Okay. Okay. So let's talk about like more conjectures. Okay, so let's talk about this conjecture. This is also exercise that says suppose xn plus yn equals to 5z n. Okay, and they are all non-zeros and all positive. And let's suppose that epsilon less than 1/3, the ABC conjecture holds. Then what? Then I can prove that okay, I can prove that n is bounded. So this is very weird that suppose if I suppose that epsilon less than 1/3, or basically suppose I believe that the ABC conjecture holds for epsilon less than 1/3, then I can prove that if this n is bounded. So basically, if n greater than something, then this equation cannot happen, right? So basically, it's the same proof as the previous. So let me just quickly make the proof. So we can check that 5z and we're less than the radical of x and yn by zn, and let's say 1 plus epsilon, right? So this is guys 5 xyz 1 plus epsilon. Okay. Right. So I think you can easily see this, right? Because x and y is less than you can control x and y less than 5 to z. So basically there's n here and then there's 1 plus epsilon here, right? So n is bounded. Okay. And okay, so another example, which is also interesting. This example says that suppose epsilon less than half, and the equation that you're worried, that you're curious, is x cubed minus 7y cubed is 1, only finite solution. Okay, so if you believe that the ABC conjecture is true for epsilon less than half, then you can prove that this equation only have finite solutions, finite integer solution. Okay, you can prove by finite. You can prove finite integer, but in my case that I works in a positive integer. Okay, so proof is also yeah, you don't need this. Okay, so I can write by the way, so one main results in one main modification in the ABC conjecture is that if a plus b, if you don't make it positive, then you just need to change this c to be the maximum of ABC. Okay, so basically you can just make this change, and the ABC conjecture should hold for all the integer. Okay, so I can make it x max, like say x cubed 7y cubed, well less than radical of x3 cubed 7y cubed 1 plus epsilon. Okay, so this radical is the radical of 7x cubed y cubed, right? 1 plus sorry, I'm right the same thing. I'm stupid, right? So this is 7 1 plus epsilon less than an x, right? So 1 plus epsilon y 1 plus epsilon. Okay, so I got this inequality. Okay, so let's say I suppose this guy is m, right? So if I prove m is bounded, then should only have finite solution, right? So I get m less than 7. By the way, I assume that C epsilon is 1, right? So I assume C epsilon is 1. It's not 1, then it's not important, right? Because if y, the goal is for me is to prove m is bounded, right? So it's m is less than something. Okay. 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 So yeah. So this is m is less than 7 plus, right? So let me just change a little bit. So x cubed minus 7y cubed is 1, right? So I know that m is basically less than 7y cubed plus 1, right? So less than 7y cubed plus 1, right? So basically this guy, this will make me some change for this x and y. Okay, so maybe a little bit hard to understand, but what I'm saying is that I can make this guy let's take absolute value. I can make this guy 7 1 plus epsilon and then change with x, right? So this is maybe m 1 plus epsilon divided by, right? So 3, and then y is m divided by 7 1/3 1 plus epsilon, right? So I get this and this. Okay, so I need to delete 1 7. So I get m less or equal to 7 2 1 plus epsilon divided by 3 times m 2 plus epsilon divided by 3. Okay, so combine everything, I can get m less than 7 2 1 plus epsilon divided by 1 minus 2 epsilon. So basically, if you assume that epsilon less than half is correct, then this guy is positive. So only finite solution. Because m is bounded. Okay. Okay, so the final example I want to say is the famous Catalan conjecture. Okay, so this conjecture is very weird that I think nowadays, I remember that 2002 that somebody claimed that proof. I think it's proof now, I'm not sure. Right, so consider x greater or equal to 2 and y greater or equal to 2. And the people want to investigate the equation like y to the n equals xm plus 1. Okay, so the solution is basically 2 to the one example is 3 to the cube is 2 to the 3 plus 1. Okay, and this is very amazing that people believe, and I remember that somebody already proved that this is the only solution if you put n equals to 2 and m equals to 3. Okay, but basically I want to claim that so I think you cannot use the ABC conjecture to directly prove n equals 2 or m equals 3 is basically the only solution. But you can use the ABC conjecture to say that in order for this guy to have the solution, which is the mn cannot be arbitrary. Okay. Okay, so except for let's say n is 2. Okay, so let's imagine that n greater than 2. Okay, so and then imagine that epsilon 1 equals to 1 and the c epsilon equals 0. Okay, so I can get the y to the n, that's the radical of y to the n, xm and 1 square. So that's then xy square. So basically it's x squared, y squared. Okay, so which says that what? So from here, I can get the x less than y n divided by m. Okay, so I can plug in here. So I get y to the n less than x squared. Sorry, y to n divided by m y cube y squared. So I get n less than 2n divided by n plus 2. Okay, so this gives me n less than 2, 1 plus n divided by n. Okay, so let's consider this equation. Okay, so by assuming ABC conjecture, then you can check that when n equals to 2, you only have finite solution, right? So for example, and let's say mn, okay, right, let's see, right? So if n equals to 2, then obviously that m can be arbitrary, right? So, but I assume that n greater than 2. So I can say that if this is 3, then if n is 3, then I guess 3 less than 2 times 6 divided by m. Right, so 1 6 divided by, so m is less than 6, right? So I can get 5 4 3, maybe 2. Maybe 2 is okay, right? But yeah, so basically you can check that if you use n to be 4, then I think there's 4 less than 2 plus 8 divided by m. Right, so m less than what? 2 4, right? So you can see that is almost no solutions, right? M can only be 3 or 2. But basically, this just tell you that now if you works in n equals to 5, then I think there's no solution. So basically, if you believe that the ABC conjecture is true, then this type of two different powers, two different integer power should have finite possible mn. Okay, and then this is a famous conjecture that people believe that the power of the integer should be infinite. So for actually, I think the famous conjecture is that this equation for any k greater than 0 should only have finite solutions, but still unproved. Yeah, but basically you can see that there's many number theory equation is related to the ABC conjecture. And if you know more about the mathematics, maybe you heard about so-called the 14th theorem. Very hard to prove. Very deep algebraic geometry says that if you have a genus curve, if a curve with the algebraic curve with genus greater than greater equal to 2, there's only finitely irrational points. And I think one can use this ABC conjecture to prove this. And also the model conjectures or other algebraic curve, but basically anything related to the integer solutions of the Diophantine equation. So maybe related to any explicit form of the ABC conjectures. Okay, so this is my very short video about ABC conjectures. Hope you guys like it. See you guys next video.